Welcome back, folks. We're going on to 12.3, day 2 now. This is called the derivative. Okay, we're going to be finding the derivative of a function. We'll explain what that means in a little bit, and use that derivative to determine where tangents are horizontal to a function. Okay, now the derivative, as we see here, is one of the most important concepts in calculus. Alright, and the first derivative of f of x, I say the first derivative because we'll talk about second and third and fourth derivatives later. The first derivative of f of x is denoted as f, the little apostrophe right there, that's not a 1, that's an apostrophe of x. I'm going to pronounce that as f prime of x. Alright, now the derivative of f of x, again f prime of x, gives the slope of the original function f of x at the point x that you plug in. Of course, remember f of x also stands for the y, so the derivative gives us the slope at whatever point we want. Okay, now by definition, the derivative of f of x, again denoted as f prime of x right there, equals the limit as h approaches 0 of f of x plus h minus f of x over h. Remember, this from our last lesson, this is the slope. So since the derivative gives us the slope at any point in the curve, if we want to, as an abbreviation, we can simply say that m equals f prime of x. So sometimes it's a very nice way to be able to say things, but there it is. Let's move on. Alright, so now I know we've done this before, but we haven't used the fancy terminology here, so here we go. Find the derivative of f of x equals 4x squared plus 9x minus 5. Okay, so again, all we're going to do, the derivative equals, okay, the good old f of x plus h thing, so I've got the 4 parentheses x plus h squared plus 9 times x plus h, and then the minus 5, and then minus the original f of x, 4x squared plus 9x minus 5. And again, that's all on top of the h, and I forgot to write it in there. Please forgive me. Limit as h approaches 0. Alrighty. So then moving on, we just have to simplify a whole bunch of stuff on top. So now the limit as h approaches 0. Okay, pardon me for doing this, but if I square x plus h squared, I'm going to get 4x squared plus 2xh plus h squared. So I'm going to distribute the 4 through there and get 4x squared plus 8xh plus 4h squared. Okay, that's going to save me an extra step, basically. Okay, plus 9x plus 9h minus 5 minus 4x squared minus 9x plus 5. Watch for sign mistakes there. There's an ample opportunity to make them. And we've got that over the x, over the h. Now again, I've got a 4x squared with a negative 4x squared, a negative 9x with a positive 9x, and then a negative 5 with a positive 5. Again, one very convenient thing with the polynomial functions is everything that didn't have an h in it got canceled. So that allows us to do some reducing here. Limit as h approaches 0. Okay, again, everybody is left has an h, so I'm just going to save a little bit of time here and now cancel one h out of everything. So this becomes an 8x plus 4h, and then plus 9, h goes away, and that's it. Okay, and again, since now I have no denominator that's going to cause me to have an undefined expression, I can plug in my 0, and there's only one h left. So the limit of this guy, which again is the derivative, is just simply the 8x and then that plus 9. Alright, so there's the derivative of a polynomial function. Let's do one more just for a little bit more practice. Alright, so finding the derivative of a rational function, such as f of x equals 4 over x minus 3, is pretty much the same process. It's just a little messier algebraically. So here we go. F prime of x equals, again, the limit as h approaches 0 of, here we go, 4 over x plus h minus 3 minus the original function, all on top of that h. Okay, and then we have a little messiness to work out. But again, basically I just need x plus h minus 3 here, all over x plus h minus 3. Again, just doing a common denominator basically. And same thing over here. I need the x minus 3 top and bottom. And again, one thing that I like to do to avoid some sign mistakes is I make that a plus and put the negative on the 4, so I'm distributing a negative 4, and it kind of, for at least me, I make less mistakes that way. Alright, so moving on, limit as h approaches 0. Okay, I've got a 4x minus 12. And then I've got a negative 4x minus 4h plus 12. And that's all on top of my common denominator, x minus 3, x plus h minus 3. A little bit messy, but there it is. and again it's all over h. Alright, so a little bit of cleanup before I get to my next step. Alright, I've got a negative 4x and a positive 4x. I've got a positive 12 and a negative 12, so again, a lot of nice stuff that doesn't have an h in it goes away. Alright, so coming back here, what I really have left is a negative 4h on top of, again, that fairly icky denominator, x minus 3, x plus h minus 3. And again, since I'm dividing by h, again, think of it as h over 1, I'm going to multiply by its reciprocal, which is 1 over h. And again, the good news behind that is the h and the h cancel each other out. So now I'm left with something that looks a lot more palatable, limit as h approaches 0, of a simple negative 4 on top of x minus 3, x plus h minus 3, which then cleans itself up when we plug the 0 into there, into being a simple, and actually let me rewrite this so it's a little bit nicer to look at for its final answer. F prime of x equals negative 4 over, again if that's a 0 I have an x minus 3 and another x minus 3, so what I've actually got is x minus 3 quantity squared. So there's the derivative of that original function right there. Alright, well, what is that good for? Well, let's see if we can find out where a tangent graph is horizontal, and maybe that doesn't seem like a very interesting thing right now, but hopefully I'll do something here that makes it a little more interesting. But okay, if a tangent line is horizontal, well of course horizontal means that the slope is equal to 0, then basically, since the derivative is the slope, and then we want the slope to be 0, basically kind of a syllogism sort of thing right there. Well, if a tangent line is horizontal, then the derivative is equal to 0. Alright, so I've got this guy. So again, I want its derivative. So his derivative is going to be equal to the limit as h approaches 0 of, again, x plus h squared plus 6x plus h, f of x plus h minus the original function, x squared plus 6x, and all over h. And then from there, I've got the limit as h approaches 0, and foiling that out, I get myself an x squared plus 2xh plus h squared plus 6x plus 6h minus x squared minus 6x. And again, lots of good stuff cancels out. X squared go away, negative 6x, and then positive 6x go away. And again, we're left with everything that has just an h in it on top. And so I can now reduce and get the limit as h approaches 0 of polynomial 2x plus h plus 6. And again, now plugging that 0 in anywhere I see an h lets me know that my derivative is equal to 2x plus 6. Okay, but again, I want the derivative to be equal to 0. So basically I'm going to take this off to the side here, and I say, well, my derivative, 2x plus 6, I want that to be equal to 0. And then quick solving gets me x equals negative 3. And then, well, I don't know where it is, so there's an x value. So, I mean, if I'm going for an exact location, I kind of need a y to go with it. So there's my x value. I'm going to circle it for now, not because I'm done, but because it's important. And now plug this into the original. Okay, because again, this is the slope of the original function is going to be horizontal when x is negative 3. Let's find out the y that goes with it. So the original function evaluated at negative 3 gives me negative 3 squared plus 6 times negative 3. And that works out to be 9 minus 18, or better yet, negative 9. Okay, so the final answer to this problem is negative 3, negative 9. Okay, so at that point, a tangent line to this particular curve would end up being horizontal. Wait a minute, what's the vertex of the parabola? Let's see that. Vertex, let's see, we had to do some x equals negative b over 2a sort of formula, right? I think that's how that worked. So I do negative 6, okay, pardon my b's and my 6's looking similar, all over 2 times a, in this case a is 1. Let's see, that's negative 6 over 2, so that's negative 3. And then while I plug negative 3 back into the original, hey, wait a minute, didn't we do this just a second ago? So when I do this plus 6 times negative 3, I'm sure heck going to get negative 9 again. So the vertex is negative 3, negative 9. That's kind of cool. Alright, so hopefully that makes a little bit of sense. If you think about just a regular parabola here, I'll just draw a very, very bad one. Alright, okay, again, if I'm talking about the vertex, Okay, again, my slope on the left side of this parabola is some kind of a fairly large negative number. And then as I start getting toward the vertex, it starts flattening out, becoming a smaller negative number. And then right about here, that's where I can imagine a tangent going horizontal. Pardon me, that one's sloped down a little bit, but you get the idea. And then past that, notice he goes positive. So if I'm negative on this side and positive on this side, well, clearly I have to be 0 right there. Got to pass through a 0 to go from negative to positive, so that's it. So basically what we just did in the previous slide is a slick little way that you can find the vertex of a parabola, not using the old Algebra 1 kind of stuff, but you can use some pre-calculus stuff. Now don't freak out, because later on I'm going to show a shortcut to getting that derivative, so you actually will be able to do it with less work than what we just did right here. But I'm going to make you earn that, so hang tight for now. Alrighty, let's take a look at another one that's a little more hairy, I suppose. Got a cubic function this time. Now again, this is a barrel of monkey's monkey, so if I just imagine a quick sketch of this thing, it'll look something like that. Alright, so again, I've got, I think, a couple different spots where this guy's going to be horizontal, like at the top of this kind of hill and then kind of the bottom of that valley right there. I'll probably end up with horizontals at those two spots. So I'm kind of, knowing what the graph looks like, kind of expecting two answers, but let's run this thing out and see how it goes. Okay, again, my derivative, f prime of x, is again the limit as h approaches 0, and again, hold on to your hat here. Okay, again, f of x plus h puts an x plus h inside of a cube, minus 27 times the x plus h, and I'll minus the original function, x to the third minus 27x. Alright, that's still all over h. Okay, now again, I'm going to assume you don't want to watch me cube a binomial. Alright, so again, this just works out to be x to the third plus 3x squared h plus 3x h squared plus h to the third, okay, minus, picking up right there, 27x minus 27h minus x to the third plus 27x. Okay, kind of a mess, but there it is, and that's all over h. Again, take out some good red canceling ink. X to the third, negative x to the third, positive 27x, negative 27x, will go away. And then again, I'm looking at the limit as h approaches 0 of a bunch of stuff that has h's in it. So again, I'm going to kind of skip a step a little bit maybe and cancel out all my h's, or at least one h out of each that term. So 3x squared, no h left, plus 3x with an h still left, plus h squared, and then minus 27 with the h gone now. And now again, I can plug this 0 into a couple different spots, leaving me with my derivative being 3x squared and gone, minus 27. Okay, but at the end of this point, what I'm looking for is to have that function's derivative, there we go, equal to 0. So I'm going to set up an equation 3x squared minus 27 equal to 0. And then factoring out a 3, or you can divide off the 3, whatever works best for you. X squared minus 9 equals 0. And so I've got 3x plus 3, x minus 3 equals 0. And then of course that gives me negative 3 and positive 3. Okay, now remember this 3 doesn't give me a solution at all. Those answers come from these two. Okay, but only gives me my x, so I do need a little bit of work for the y, but since I've run out of space, I'm going to take this to the next slide. Alrighty, so picking up with my x equals negative 3 and positive 3, and now remember our original function was this guy. So again, all we have to really do is now plug these two different x values into here, and we'll get two different points. And if you remember, that's kind of what I was expecting to get, knowing that this guy looks like my barrel of monkey's monkey. I don't know exactly where he goes. Let's just pretend he goes something like that. So again, I know there's two spots, and apparently one of these is at negative 3 and the other is at positive 3, where our graph kind of goes from up to down and vice versa. Alright, so let's just do the negative 3 first, just because I listed it first. So for x equals negative 3, alright, I want f of negative 3. Again, remember we're going back to the original function here. So negative 3 cubed minus 27 times negative 3. Alright, and so that's going to be a negative 27 plus 81, and that equals a positive 54. Alright, so one of my 2 points is negative 3 comma 54. Alright, I got a second one though, for x equals positive 3. Alright, so f of 3 equals 3 cubed minus 27 times 3. And conveniently, I'm going to get some similar numbers here, 27 and negative 81, and that gives me now a negative 54. So my other point, where my horizontal, my tangent is horizontal, gives me 3 and then negative 54. Alright, so again, those are basically the 2 points on this graph where it changes from going up to going down and then to going back up. And that's kind of a nice thing the derivative let us do, is give us some good information about how to draw a graph by hand. Ooh. Alright, but anyway, there you go. There's the assignment. Give those a shot. And of course, as always, ask me any questions you have in class. See you then.